Ça marche.
Ben voilà, juste pour dire deux mots sur Aristide, je pense que tout le monde te connaît plus ou moins. Tu es étudiant, Aristide est étudiant en thèse au LERMA avec Benoît Semelin, et il travaille sur l'époque de la réionisation. Déjà en troisième année, hein, c'est ce que je discutais.
Oui, déjà, ouais.
Le temps passe très vite. Et voilà, aujourd'hui, il va nous parler un peu de son travail, et en particulier des méthodes d'apprentissage supervisé. On t'écoute. Tu nous fais en anglais?
Comme vous voulez, ouais, je peux, ouais. Enfin, j'ai prévu ça, mais si vous voulez en français, je peux aussi.
Parfait.
OK.
On t'écoute, merci.
OK, so hello everyone. So as Philippe said, I'm Aristide Doussot, and I'm a third year PhD student at the Observatoire of Paris. And today I will talk about what I did during the first part of my PhD, meaning how to use the supervised learning methods to reconstruct parameters of the epoch of reionization. So I did this work under the guidance of my supervisor, Benoît Semelin, and I will also talk about the results, the connected results of a previous PhD student of Benoît, Evan Eames. Okay, first of all, a little bit of context. So in our team, we are kind of old people because we are interested in a faraway epoch, which is the epoch of reionization. So beginning at a redshift around 25 and ending at redshift 6. And during this epoch, the first stars, the first galaxies are forming and are starting to ionize the medium, the universe. And so we want to study it, and in particular, we are interested by a signal, an observable, which is a 21 centimeter signal. So it comes from the hyperfine transition between the two ground states of the hydrogen. And it's a relatively complex signal because it's, first of all, we see it as a fluctuation compared to a ground signal, which is the signal coming from the CMB. It depends on the ionization fraction, on the density, on the temperature, also on some cosmological considerations. So it's a complex signal, and basically what we can have thanks to simulation, not yet with observation, we hope for SKA, but for night simulation, we can have something like this. It's a light cone where we can see the signal. So as you can see from the color code, it's a fluctuation, sometimes positive, sometimes negative. So you have the redshift in the x-axis. And we can get from this light cone, which has the full information, some statistic quantity. Here we will be interested by the power spectrum. So we directly choose to reconstruct the parameter that I will show you just after, starting from the power spectrum and not the full signal. So we already assume that the non-Gaussianity were not relevant, or at least were negligible to reconstruct the value of the parameter. So to get this observable, we basically use model. So we had to choose what model to use. We could have used our own models, the model developed in our team. So it's a radiative hydrodynamical simulation, Licorice, which has, as a matter of fact, a small database, which is called 21 centimeter SSD, which is composed of like 45 simulations with different value of the astrophysical parameter, giving us different observables in the end. But 45 points, 45 simulation is far too few for machine learning, for supervised learning in general. So we decided to use another model, which is 21 centimeter fast. It's a semi-numerical model, so it's making some rash approximation, but as a counterpart, we can run it like a lot more than our fully numerical model. And basically, this model is based on many parameters, but three are relevant for us, the three parameters that we will try to reconstruct with our methods. So the critical temperature to form star, so it's called Lyman limit system influence, but it's basically the mean free path of the photons, and the ionizing emissivity. So basically, right now in our fields, when we want, starting from an observable, a signal, to reconstruct the parameter, we are doing basically Bayesian inference. So Markov chain Monte Carlo techniques, basically doing hundreds of thousands forward modeling, comparing our output signal to the signals that we want to reconstruct, and so adjusting the parameters. So that's very, very costly. And for those of you who are familiar with a supervised learning method, it can be replaced by a backward method, a supervised learning method, which takes the observable, the unknown signal, and reconstructs the value of the parameters, giving birth to this signal. So we were not the only one to try to do that. In fact, supervised learning, I've been for the past few years, it has been used a lot in the 21 centimeter signal field, both as emulators to totally replace the computationally costly models, or like us for parameter predictions. So there is kind of I think that almost every method of supervised learning has been tried, especially for emulators. You have a little list of reference here, but for parameter prediction, it was most scarce. There was the first attempt was from our team, from a previous postdoctoral, who was Ayato Shimabukuro, who tried to reconstruct using also power spectrum. We can also cite Nicolas Gillet, who use the whole light cone, and also a team in America who try to use image cubes to reconstruct the parameters. But for us, let's go back to our problem. We want to reconstruct the parameter using supervised learning, and it's first of all for machine learning auditors, it's a regression problem. It's not classification. We're not like in classification of galaxies as 0 as 1. The value are not discrete, they are continuous. So that's kind of a tricky problem that we can solve, but that's not the same problem as just picking a class between some. So our first try, of course, when we look at supervised learning methods, the most popular and maybe most powerful one, it is to discuss, but maybe most powerful, that's neural network. So in a neural network point of view, in a machine learning point of view, our problem is the following. We have the value of the power spectrum for 10 redshift for 12 web number. So the value of the power spectrum for 120 bin. And we want our method to map this signal, so a 120 dimensional signal space, into a 3D parameter space, which is composed of the value of our three parameters. The first thing to emphasize that I want to emphasize here is that it's relatively low dimension for a neural network. It sounds like a lot. I mean, I cannot think in a 120 dimensional space, but for neural networks which have been designed, which have been like optimized to treat like basically pictures, it's really low dimensional. If I want to make a picture of my input, it will be a 12 by 10 pixel picture in black and white. So that's not so much. So we tried, of course, many architecture with convolutional layer, locally connected layer, but for such a low dimensional problem in terms of neural network, we did use that a simple architecture is sufficient. And in fact, we picked the simplest one possible, which is a fully connected neural network with only one hidden layer composed of 80 neurons with 3 neurons in the output layer, each one giving the value of one of the parameters. It doesn't look like a lot, but it's already more than 9,000 free parameters, free weights and bias to adjust. That's in opposite a lot of parameters, but it's a nonlinear mapping, so that's kind of okay. The point is, it has been mathematically proven that given a sufficient number of neurons, one layer fully connected neural network can approximate any function. So there is ground for success here. I also want to precise our learning set and our training sets. They have been composed of, for the learning sample, of 2,040 examples. So and 40 simulation, 2,400 simulation from 21 centimeter fast, and that's again not a lot. We were able to produce them far more data points than with fully numerical simulation, but 2,000 is not a lot. And we have another problem. Usually, when your learning set is not high enough, a good way to improve it is to use some symmetry of your problem. Basically, if you want your neural network to recognize cats, you can take the pictures of your cats and make some rotation. I mean, it's still a cat, even horizontally. You can make dilatation, like zoom on your cat, it's still a cat. Here, we cannot do that with power spectrum. We we cannot just shift the power spectrum up and down. That will not correspond to the same situation in astrophysics. So we cannot do this artificial increasing of our learning sample. So we had to adapt to this relatively small learning sample. As a test sample, we took 500 more examples. So the good point was, with a small neural network and a small learning sample relatively, it was really, really fast to train. So that was our good point. But yeah, there is a numerous disadvantages about that. So for those of you who are interested in the architecture, I just put in this slide the characteristic functions that we use for a neural network. I mean, every characteristic of a neural network. I will not go into further detail here. You can, I think, yeah, there is a video on YouTube, so you can just make pause and look at it in full details. But yeah, for those of you who are interested, there is the characteristics. And so now that I briefly explained the problem and our tool, let's talk about the results using its tool. So first, let me introduce the previous results from my team, so from Ayato Shimabukuro. He used a neural network, fairly simple, with a low number of neurons, neural network, and he gets a reconstruction error of about 20%. So what you have here highlighted with the red square is basically the mean squared error for the reconstruction for the 3 parameters. So around 20% of reconstruction error. And this graph is kind of a well-known graph in a neural network field. It's basically plotting the predicted value of the parameter as a function of this true value. For the test set, we know the true value, so we can do this plot. And basically, the closest the red cross are from the black line, the better the prediction. What we can see is it's not random at all. Yeah, it's predicting something, but it's still, yeah, little blurry. We can see this 20% error in a reconstruction. For our best network, so the ones that I briefly described above, here is a plot, so the predicted as a function of the true value. So we can see by eyes that it's better, but as is, yeah, it's qualitative. So in a more quantitative way, the root mean squared error shows us that we gain an order of magnitude in accuracy, basically going down to a 2% reconstruction error. First, I want to emphasize that that's not just by some magic. It's just because we had a little bit more data in our learning sample. We had a little bit more neurons. We made I think, a wider exploration of the hyperparameters, the characteristic function, and so we were able to gain this order of magnitude. Secondly, I want to emphasize that 2% it's already pretty well. When you're doing it's to some extent, when you're doing a classification problem, you have 4 or 5 classes. If you're able to select, to label each of your if each of the elements of your test set in one of the class with a 5% error, it's already good. So here we have 2% error. It's already good. Furthermore, during our investigation, we made accidentally some retro engineering. In fact, that was a prediction of our best network before we correct the problem. And we can see that for the mean free path, it was predicting a kind of a stair function. Whereas we wanted to predict like the black lines, a linear 1-1 relation between the prediction and the true value. It was predicting a stair function. And it was so strange, so particular, that we decided to investigate it. And in fact, it uncovered a degeneracy in the model that we didn't take into account. So I will not go into details about the 21 centimeter fast simulation, but basically the value of the mean free path only affects the output signal on an interval of value. So if the mean free path is 9 megaparsec or 11 megaparsec, it's basically the same for the simulation. And that was what our network did tell us. So we were able to do some retro engineering, which is a kind of a good results. Our network was able to detect a feature of the code that we didn't take into account. And so we were kind of satisfied, but we thought we could do better than 2% reconstruction error. And so even if it was good, as a far greater man than me once said, if better is possible, good is not enough. So we looked into supervised learning methods to other supervised learning methods. Again, we were on low dimensionality for neural networks, so there might be somewhere another supervised learning method more fitted for our dimensionality or a small sample. And so we looked at sums and picked the regression. So you might say regression like linear regression. Yeah, exactly, like linear regression. So we first try with a linear regression, which is, yeah, a supervised learning method. In fact, if you remember, linear regression is basically minimizing this quantity. So you have your output here, your input here. You're making a linear function of your input, and you want to be the closest possible to the output. So you have some weights, beta and alpha, and you adjust your weights on your learning sample. It's a supervised learning method. It's not so simple, in fact, because it's a linear regression. Okay, but I remember you that we are in a 120 dimensional signal space and a 3D parameter space. So that's a linear regression in yeah, in big spaces. And when we train this linear regression and compare its performance using again the mean squared error, you can see here on the last line that we are already better with this linear regression than the first network that we use with Hayato Shimabukuro, but still worse than our best neural networks. And that was kind of a relief at this time, because I spent weeks, months, like making the best neural network. So if a simple linear regression had outperformed it, I would have been like rather disappointed. So it was not enough, but again, it was a linear regression. We could improve it. First way to improve it is to use what is called a kernel regression. So mathematically, it's basically weighting your various points of your learning sample by a kernel, by a Gaussian, and basically you give more importance to the point of your learning sample that are close to the ones that you try to predict. So if I do it schematically here, you see that that's the weights. And so you're doing a linear approximation, which is very good locally. And so you make a better prediction. So that's the theory. In practice, it works. So that's great. And when you see the mean square error here, you can see that we perform better than with a simple least square. We are of the order of the reconstruction accuracy for one parameter, but far worse for the two others by a factor of 2 or 6. But never mind. Again, it's a kernel regression. We can do better. And that's what we did. We went and looked for something called ridge regression, combine it with kernel to create a ridge kernel regression. And basically, it was about adding to the quantity to minimize this quantity, which will be which will be familiar for a neural network user in the audience. It's basically a regularization term. What you do is you want to minimize also the quadratic sum of your weights, modulo some amplitude, and that allow you to be very quick to get rid of some degeneracies. Basically, if your output is only sensible to combination of your inputs and not their absolute value, it will allow the network to speak the solution with the smallest weights, with the smallest weight. So when adding this regularization, again, we're gaining some reconstruction. We are better in reconstructing, and right now with the ridge kernel regression, we are better than our best neural network. Better to the point that it's basically the reconstruction error is basically of the order of the percent. So that's pretty great. But we thought that again we could do better. We could do better by locally determining the hyperparameters, meaning that the amplitude of the regularization term. We set it to some value, but we can let the code, the method, set its own value, pick the best value it can compute. We also have a sigma here, so basically the width of our local kernel, which give weights to the points of the learning sample. We can let the method adjust the weights too. And when we let this liberty to the method, it performs again far better. Here, right now, we are a reconstruction error below the percent of around 0.5%. But I want to highlight the fact that for this case, it's only a theoretical accuracy, because to determine the best value of the sigma and of the lambda, we need to inject the true values that we want to reconstruct for our test sample. So we use the fact that we already know the answer to fit the function to give you the answer closest to the ones that you already know. So it's a little bit of cheating, but not so much, because what we will do if we have an unknown signal, a real signal that we want to reconstruct, to constrain, we will basically determine the closest signal from this unknown one in our learning sample. Look at, okay, for this closest signal, we have the hyperparameters coupled that gives the best results, were these two. So let's apply these two to our unknown signal. So there will be a slight difference. So it will be slightly worse than our best theoretical accuracy, but it will still be like better than our canal regression without this fitting. So we did an extensive analysis of the possible value of this couple of hyperparameters. The relative simplicity of our model, of the relatively low number of hyperparameters, allow us to do that, and that was something that was also attractive in rich kernel regression, is that we have better understanding and control over the whole process. So yeah, that was our best result. So 0.5% reconstruction. We are really happy. So if I show you the plot predicted as a function of the true value, it's really on the black line as much as we don't see anything anymore. So let's switch our representation and go to the relative error, basically plotting the prediction value divided by the true value as a function of the true value. So I put that here. I also put the predicted SKA thermal noise. So the uncertainty on the measurement of SKA, and you see that the uncertainty of our reconstruction is negligible compared to the already existing uncertainty on the signal. So that's kind of good. That's kind of good, but we were again in theory, in the theoretical world, where given the right assumption, you basically obtain everything you want. And now it's time to face reality. And in reality, the signal that we will obtain will be noised. In fact, right now we only use pure signals, and so the noise will make things harder, like a lot harder. In this plots, you can see our power spectrum for all the beams that I told you before. So at 10 different redshifts, at 12 different wave numbers for 10 different redshifts. What you can see, the black line here, that you can see here, here, and here, it's the pure signal when it's not noise. And the color lines, yellow, orange, blue, all the color lines are basically noisy realization of the unnoised black signal. What you can see is that we lost a lot of information because of the noise. Oh, sorry, I don't think I precised it. We emulate the predicted noise of the SKA instrument. So yeah, we are losing basically all the information at high wave number. We keeping some information at low wave number, but it's kind of half of the beams that are like totally too noisy to get information. And yet we want to reconstruct the parameter with this. So we say, okay, you know what? Never mind. Let's make some noisy realization of our unnoised signal, train the same methods on it, and look at the results. So that's what Ayato Shimabukuro did. That's what I did. And that's what gave us a 10% reconstruction error. Of course, because the problem was far more complex. You had to, the network, the methods have to kind of denoise the signal, and then with their denoised signal, reconstruct the parameter. There is one more step, one difficult step. So 10% error, not so good. We want to improve it. How to do it? Basically, we believe that our methods were not the main thing to change. We believe that we have to work on our learning set, on our sets, to make easier the work of the methods. So we did first thing first. We did something very well known in astrophysics. We weighted our signal by the variance of its noise on the considered beam. So basically, for some wave numbers, the noise is very high. We divide it by the variance of the noise. So basically, the signal is put to 0. Whereas for other beam, where the noise is not so high, we kind of keep the signal. So basically, what we're telling to the network is, okay, do not learn here. There is nothing to learn here. Focus on this part, which has been magnified by the weighting. And when we do that, we have a progress. It's easier for the methods. So basically, we have a progress. You can see them here. Compared to a noisy reconstruction with a 10% error, we are now around 7-8%, depending on the parameters. We had a gain, but it was not a humongous gain. It's only 2%. That was not enough. So we thought about it a lot. In fact, on the contrary, from what I told you, we tried other supervised learning method, other neural network, able to denoise, make some combination, a denoiser and then a predictor. But at some point, we really realized that there was a theoretical problem that we didn't take into account, and that was like biasing or evaluation of the accuracy of the network. So I will explain it very quickly. It's rather like obvious when you know it, but I can assure you what you didn't pick it up, it's kind of hard to find. Basically, it's what I will call the noise stochasticity problem, and it can be explained by the fact that a noise signal can come from various unnoise signals. That's why when you have a Markov-chain Monte Carlo reconstruction, you have a whole range of values that are predicted with some performance. And right now, our methods are only able to predict one value. Basically, we want them to predict the maximum likelihood value. But they are able to predict only one value, whereas there is many possible values. So basically, with a toy model with one parameter in a 2D signal space, it can be expressed like that. So the noisy signal P can come either from this unnoised signal with this realization of the noise, or this unnoised signal with this realization of the noise. But the most likely unnoised signal that this signal is coming from is this one, basically the one for which the noise is the lowest. It's the maximum likelihood. It's the most plausible signal. And if you look at this toy model, you can see that basically it's geometrically the closest unnoised signal from the noise signal that we want to analyze. And so we pick that up, and we had to modify at least our test set, because when we were feeding on network with this noise signal, we were telling it, let's take an example, this signal P. First, it had the signal P corresponding to this noise signal, so this parameter. And the network, even if it has learned perfectly, it will tell us, okay, you give me this noise signal, it corresponds to the parameter theta prime. And we were telling it by construction, no, we get this noise signal starting from this noise signal. So you had to find theta 0. So we tell him that he has an error of this amount, whereas there was no error. Same thing for the second time, it will encounter this noise signal coming from theta 1. It will say, okay, the most probable one is theta prime. And we will say, no, it comes from the noise signal we form with theta 1. So you should have found theta 1. So you can see that we have overestimate the error, the reconstruction error of our network, just because we were not paying attention to what it was supposed to find, in fact. So how to correctly evaluate the accuracy of our networks by basically using a test sample where the noise have been perpendicularized. So geometrically on our toy model, it's fairly easy to see. And basically, we're using only noise signal that most probable noise signal correspond to the one that has been used to create them. So perpendicularized signal. And then when it fills this noise signal to a network, it will tell us what parameter it should correspond to. And we will be able to say, no, okay, the most likely one was theta 1. If you don't have theta 1, you are wrong. It's not us. So with this new way to evaluate things, we in fact were much better than we thought. So with a perpendicularized sample using a neural network, you can see here that's compared to before. We divide our error by a factor of 2. So we are now reconstructing a parameter with a 3% error. That's already great for such a noisy signal that you could have yeah, that for such a noisy signal. So here is my relative error. So the blue line is basically the mean squared error, but for bin of value. What you can see is that we are basically, our reconstruction error is basically half the uncertainty on the measurement, basically, due to the thermal noise. So that's not negligible. But neural network not our neural network wasn't our best supervised learning method. Our best one was using regression. So for the rich kernel regression, we used it. We were better, again, like 2%, 2 or 3% prediction error. And then one step further, or locally, when we're using your rich kernel regression, but with all the local determination of our hyperparameter, we're going back to the percent of reconstruction error. So we were kind of happy because starting from such a depleted, such a corrupted signal, we were kind of happy to have a reconstruction error of only 1%. If you look at the bin chi in the plot, you can see that it's now around, like, the reconstruction error is around 10% of the SKA thermal noise. So is 10% negligible? That's kind of a philosophical question, but that's already okay to reconstruct the value of the parameter starting from the signal without adding too much error. But yeah, so we were kind of happy with that. Yeah, that was our best results that is our best results. But we were also so as you could see, we were really bothered by the low dimensionality of our problem and the low number of our example of our data. For that, there were PhD students before me, Ivan Ems, who tried to do what we will call a sample optimization, basically trying to take values of the parameters, a set of triplet of parameters that will give you the more values, the more information. To give you a quick example, if your parameter equal 1, if a given parameter equal 1, and you have a signal, when it's equal to, if it's the same signal, you kind of lose your second point because it doesn't change much between the value of 1 and 2. So you put 2 points for the same signal. And maybe between the value of 2 of your parameter and the value of 3, the signal will change a lot. So it would have been better to basically just put 1 point at 1.5, and in the close range where everything changed, where there was a lot of information, put more points. So that was our thinking. And basically what we want to do, what they want to do, was to create a sample in the parameter space such that the distance between two neighboring points of the sample in the signal space is the same. So when you're having your distance as the same in your parameter space, it's basically a grid. You pick your point on a grid. You have the same distance on the parameter space, but yeah, maybe it's not at all optimal on your signal space. So what they did was to basically define a distance in your signal space, so a basic L2 norm, define a metric, and starting from this metric, so compute a lot of information, Fisher matrix and stuff, and try to basically find the best gridding possible to optimize the information with the same amount of points. So they call that the average eigenvector sampling. And what was great at this time is that we have our neural network ready to try to learn with the basic logarithmic grid sampling and with this average eigenvector sampling. We did it, so we trained the same architecture, exactly the same parameter, except the learning set has been changed. We trained 2 neural networks. The one trained with the logarithmic sampling perform in reconstruction worse than the one trained with average eigenvector sampling, meaning logically that there were more information to learn in our new sampling with the same amount of points than in the previous one. It performed better by a factor of, I don't know, by 10%. It was like 10% better on the prediction. If the prediction error was around like 2% for the grid, it was around 1.8% for the new sampling method. They also decide to try another optimization of the sampling by getting rid of the grid totally and basically generating an adaptive grid-free sampling, and with a very simple logic. Basically, you first you're taking your amount of points and you put them randomly on your parameter space, and then you compute the distance between two close points in the signal space. If this distance is too short, they are patched away from each other, and then we compute it again. If it is too close from another point, they are pushed away. And thanks to this kind of, it's not dynamic, there is no acceleration of force, but thanks to this kind of dynamical way of pushing away points from each other, in the end you get a signal space that is like, that is populated with points that are at the same distance and where you have maximized your information. So we also tried on neural network with this method, and we had like 15%, I think, improvement of the reconstruction compared to the simple grid. So there were more information in this way of grading than in the more basic grid-based one. So yeah, I think I will stop there. I will just briefly summarize what we did. So basically, for a noise-free signal, we were able to improve the quality of our prediction by a factor of 50 compared to our last studies with Ayatoshi Mabukuro, thanks to the use of another supervised learning method, which is not neural network, but kernel regression, which appear to be more fitted for our problem. This reconstruction error is below the percent in the best case, so it's relatively negligible compared to the already existing thermal uncertainty about the signal. Now, when we go into the noise signal, we want to highlight the problem of how to correctly evaluate your prediction accuracy. Basically, doing a perpendicularization of the noise to disentangle between your network error and just the thermal noise. So even for a noise signal, we have an improvement of the quality of our prediction by an order of magnitude, meaning that we can predict the maximum likelihood value. So right now, only the maximum likelihood value with only 1% reconstruction error. It's 10% of the uncertainty about the signal. So is it negligible? We already discussed that. But yeah, all of these results have been summarized in a paper that we published a year ago, but it was December 2019, so a year ago. And yeah, we believe what's next, because it obviously can be improved, we believe that we can use Bayesian neural network not to only predict the maximum likelihood, but the whole contour. That could be an improvement, a strong improvement. Also, we already did a lot of things to be able to extract the maximum information for like a relatively scarce learning set. So maybe using even fully numerical simulation results, which are like, there is even less points in this simulation that we had with our semi-numerical simulation. But we know maybe with all of our techniques, we might be able to reconstruct it more accurately, even with a even lower number of points. And also maybe adding more information. I will be very careful about that. If someone wants to know more, we can discuss it. But basically, maybe using not only the power spectrum, but the bispectrum, which counts non-Gaussianities, or I don't know, the scattering wavelength transform, or even using something that a latent vector that has been given to us by a generative adversarial network. Yeah, we can try that. Granting that some people already tried it with the full information of the light cone, and it appears that it's kind of too much noise to use all the light cone, and there is too much unwanted information for the network to be able to only pick the relevant one. Okay, so that's all for me. Thank you for your attention.
Thank you, Aristide. Do you have questions for Aristide?
Well, maybe I can ask a question. Maybe I've not missed something, but you said that there's 2,400 examples.
Yeah.
But this is almost easy way to, it's not a full identical simulation. So you could have twice or 3 times more easily, no? Is it possible? Or?
Yeah, absolutely. It's kind of, it's physically possible to run this to run more simulation with like a sufficient amount of time. But when I say 2,400, of course, the more information you have, the more data you have, the best you are. But it's by order of magnitude that we lack data to some extent. Basically, when they're doing when Google, I don't know, everything is going classification regression problems, they are dealing with millions of data. So we could have increase our data set, but the problem would have been, I think, the same. And our point was to develop a method, an efficient method with not so much data. So increasing the number of data would artificially improve our accuracy, but that was not our point in a way.
And finally, you can have 10 times more order of magnitude, 10 or 100 times more.
You mean if we run it like for years, for like months on multiple CPU, and we could have. Okay, there is a temporal problem in that, is that I have a limited amount of time to do my work, but but yeah, we could have.
Okay.
So how fast are the methods? I mean, what is the bottleneck? Is it the simulations, to run the simulations, or the?
It's I think it's absolutely running the simulations to train the network. Okay, I said it in one slide, but basically with the neural network and the little amount of data, it's maximum a few hours to train the network, starting from a totally blind network. So training it is not computationally either costly because it's one CPU, or long. So it's basically getting the data. And of course, for the research part, is basically obtaining the best network. So that takes time. but one precision for the supervised learning method for the linear kernel regression, you're doing the regression on each unknown point. So it's not like the neural network where you have trained it one time and then you can apply it to everything. Basically, you have to for the rich kernel regression, train it for the specific points that you want to fit, because you know the locality you want to be able to very fit your space locally to the unknown points that you want to predict. But even from this one, I think it was even faster to train the kernel regression than it was for the neural network. So that's not at all a problem. The computational cost compared to a Markov chain Monte Carlo, for example, it's order of magnitude faster.
I had another question about the noise. You said you generated the noise from the SCAF, from the instrument. How far is it from reality? I mean, what do you in the number you provide with your conclusions? Is it something that you could expect to be close to the reality, or is it?
You mean is our way of emulating the SK thermal noise will be close to what we have?
Yes, I mean, how simplified is this? How would you qualify the?
Okay.
To see because you show a very good agreement, but
if it's even more noisy, if it's even noisier, what would be
for example,
the outcome? Yeah. So first of all, you see that it's increasing like almost. I will show you the. Yeah. So you can see that it's increasing almost like exponentially as the noise with a increasing wave number. Basically, you have kind of no noise for 10 minus 1 and a lot of noise for 1 centimeter minus 1. So I think even if we have underestimated the noise for this region, we have already given up on them. So for this one, it will not be a problem. For the ones that have, like we predict low noise, it will be more of a problem if in fact there is much noise that's predicted. But so for the details of how we emulate the noise, so I can send you back to the paper we wrote apart on how we emulate it. I will also maybe use my joker, Benoit, because he was the one who helped me to do this part. So maybe he can answer you better about that. But I think we theoretically take into account. Yeah, maybe Benoit, do you want to add something? But I think it's
Yeah, well, the computation of the thermal noise, I think, quite is done quite seriously. It takes into account the exact layout of the station, of the SKA, the effective area, the elevation of the field in the sky. So the thermal noise, I think, is computed quite correctly, but it's necessary to mention that some other kind of nuisance, like uh, imperfect foreground subtraction, imperfect ionosphere corrections, could add additional sources of noise, which would not be thermal noise. So this is okay if all other instrumental nuisance parameters are completely corrected for.
Antoine?
Thank you. Hi, thank you for the great talk. Can you hear me?
Yes.
Yeah, yeah.
Okay, thank you. I have a question related to what you said at the end of your talk,
Yeah.
which is that you could also decide to try to get the information from an higher order statistic like the RWST. But I think the fact that you've put many thoughts on trying to extract what you want to extract from only a 1D power spectrum. It's not even a 2D power spectrum, which basically is just telling you about the energy in the image as function of the scale. But the fact that you reach such an accuracy is probably telling you something about the underlying physics of your signal, of your images. So my question is the following: do you expect it from the physics of the reionization to have something that is like Gaussian without anisotropies? And do you expect it to evolve with time? Like if you take a redshift 6 or 7, do you expect it to be like less Gaussian than a signal at redshift 10? Yeah, that's it.
Okay. So first of all, yes, we didn't, as you said, we didn't take into account other type of signal by spectrum because there were no need. In fact, we had already a good accuracy with only the power spectrum. So we said, yeah, so maybe the non-Gaussianity are not so important for the reconstruction of the signal. I want to emphasize the fact that our signal, the 21 centimeter signal, is kind of a tricky signal in the fact that it is emitted from neutral hydrogen atom, and at the end of the reionization, there is no more neutral hydrogen atom. So basically, at the end of the reionization, we do not have the signal anymore. So it's a kind of a signal that starts from 0 during the reionization, vary, or even a little before the reionization is varying, and then go back to like 0 signal at the end of the reionization. So at the end of the reionization, we do not expect any signal whatsoever in some way. So so it kind of answers the fact that it will not be more non-Gaussian at the end. So as I am still a PhD student, I don't want to be so too sure of myself, but do we expect the 21 centimeter signal to be basically Gaussian? Okay, I will say for me. I will not speak for anyone in the field because I'm sure there are better experts than me that will be able to say why we expect or why we do not expect the signal to be Gaussian. For me, it came a little bit as a surprise for me that it was so well described, in fact, that we are able to reconstruct it so well with only Gaussian information. Because as you can see from the equation of the 21 centimeter signal, it's a rather complex physical signal. It depends on a lot of things, on the density, on the local ionization fraction, on the cosmology. So for me, thinking that all these different inputs, this entangled physics, it can be like, yeah, the information is mainly at a Gaussian level. It was kind of a surprise for me, I think. but I will not. I will not speak for my whole field. Maybe.
Thank you.
Philippe, on t'entend pas.
One word.
Yeah, just wanted to add one or two words in relation with Antoine's question. First, we know that the signal is non-Gaussian. It's been computed, well, at least in numerical simulation. And the point is that we used semi-numerical models that may possibly underestimate the non-Gaussianity of the signal. So it's not because it worked really well with those signals predicted with somewhat basic models that it would be the same if we had used full numerical simulation. And that's also an answer to Francois' previous question. Of course, we could have used 100,000, probably given enough computing resources, we could have produced 100,000 signals with this code. Doesn't mean that we could do the same with numerical simulation. And our goal in the end is to work with signals produced with full numerical simulations. So that's quite an important thing. And just Antoine, actually the signal we really use is 1D okay in the sense that is a isotropic power spectrum, but it does depend on two variables, both the wave number and the redshift.
Oh, I see. Yeah. Okay.
Kind of a temporal dimension.
Mm-hmm. Thank you.
Any more questions for Aristide? No? So thank you very much, everyone. And we see you next week with Rodrigo, who is here. Hi, Rodrigo.
Very nice talk. Thank you very much.
So see you all next week. Thanks.
Yeah. Bye.
Bye.
Thank you. Bye.